In the past, all the motion in the universe that we can see from our backyard has been attributed to everything going around the Earth. Now that we know that the Earth goes around the Sun, those motions become a little bit different. I'll start talking about Tycho Brahe. He was what is considered the most detailed observer of astronomy of his time. He had something like 20 years of data of very, very carefully measuring the motion of the planets and the stars. Okay, I got to tell you about this Tycho Brahe guy. He was, in what we would use in modern terms, he was a party guy. He always had banquets and lots of people and was very extravagant. Very extravagant is a very good description of him. He had a golden nose, as in he lost his nose and had a prosthetic made. In 1901, I think it was, they exhumed his body, which is in Italy, and yeah, there was a golden silver, I believe, prosthetic nose that was like, right here, the bridge of the nose. And the story is that he, during one of his many parties, had a drunken argument with somebody, and it was broken up, and then later in the night they decided to fight again, and they were going to have a duel. Now, duels were kind of a thing back then. It wasn't necessarily to kill somebody, but it was a fight to show who was right. And they went outdoors, and you can imagine a lot of alcohol involved. And outdoors then, there wasn't a lot of light, so it was fairly dark, and they had a sword fight, and he lost his nose in this duel. What was the argument? Who is the better mathematician? Yeah. So Tycho Brahe also had, this reputation, and there's another story about how he died. The story is that he was at a banquet and was too polite to the host to get up and use the restroom. And several days later, he died from what people thought were an exploded bladder. In 2010, they exhumed his body again and did chemical analysis and determined that he had some condition where your bones would fuse together in a weird sort of way. So it was something that happens today, and they recognized, he had this, but it wouldn't have caused his death, but it could have caused other complications. They looked at, I believe, isotopic ratios in his bones to try and figure out his diet, and it turned out he had way more protein than the average person of that time. From this analysis of his bones in 2010, they've determined that he was obese, and probably very obese, and might have had diabetes, and basically died of maybe alcoholism and obesity and just everything put together. But probably was not his bladder, but it's still quite a story. Honestly, I'm drawing a blank here. I cannot remember what country he's from. I said something about Italy, but I don't think that's right. I want to say modern Czechoslovakia, because the tradition there is if you are eating dinner and you have to get up to go to the bathroom, people will say, "Excuse me, I don't want to end up like Tycho Brahe." So they use that excuse today, even though probably wasn't true after all, but still a great story. Now this other guy, Johannes Kepler, Lord, stupid autocorrect. Johannes Kepler. Now this other guy, Johannes Kepler, was basically the exact opposite of Tycho Brahe. He was extremely religious, and not the type of religious that everybody agreed with. He got excommunicated from, I believe, 3 different countries. So he kind of wandered and found Tycho Brahe and really recognized the value of the data that Brahe had taken and was desperate for it, but Brahe wouldn't give it to him. So naturally, he became part of the household, which I guess was the thing back then, and spent years with him. And you can imagine this guy who's very pompous and I guess you could, I don't know how you would describe him in today's terms, but definitely the opposite. Ended up staying with him and becoming friends with him just for the data. So he was he was using him. But Tycho left such good data that Johannes Kepler was able to analyze and study this data and came up with a new understanding of the motion of the planets. So we look at these today as what we call Kepler's laws. We used to believe from Aristotle's time that planets were moved in circles. And from Brahe's data, Kepler figured out that the motion of the planets is ever so slightly elliptical. It is almost a near perfect circle, but it's not a perfect circle. There's a little bit of an ellipse to it. So the other thing he noticed is that the planets didn't move at constant speeds around the sun. And it took him a long time, but he realized what's happening here is that as the planet orbits, the area that the planet orbits is related to time. So in this little animation, you can see these little triangles are getting skinnier, but they're the same area in each of those. And then if you look at the planet itself, right along here, it is moving slower and slower. And then the last one is a little bit of math. It says that the period of the planets, and period is the time it takes to go around, is proportional to basically the distance between those, between the planet and the sun. So the further away you are, the less time it takes for you to go around. So something that orbits close in would orbit really, really fast. Something that's far out would orbit a lot slower. And we actually will see this in looking at the planets themselves. So there's a little bit better picture explaining some of this. Each of those triangles is equal area, and I think you can see the motion. It's moving fast and then slowing down. I think that's a little bit easier to see that. Mercury goes around the sun. It's the first planet in less than a year. Earth takes a year. Jupiter takes, I want to say, 12 years, 17, 18 years to go around. Pluto has not gone around the sun since it was discovered in the 1930s and then later got demoted in 2006, but it takes a few hundred years to go around. We've actually found an object orbiting the sun, and we think it takes about 10,000 years to go around the sun. So that allows you to say that this is really, really, really far away. Now, NASA uses something called the slingshot effect, which uses Kepler's second law. That's really cool. They'll launch something into Earth's orbit, and then they'll fire a rocket engine so it goes up higher away from the Earth, and then they let it fall back to Earth, but fall in such a way that it's going to like miss the planet, because otherwise that'd suck. But as it falls toward the Earth, it speeds up and goes faster and faster and faster. And around the other side, they fire the rocket engine again to sling it higher up so it gains more and more speed every time it does this effect. And then eventually they fire the rocket engine away from the Earth and take off at really high speeds. So we'll use this effect. Things that go to Mars and other planets typically will spend a month or three in Earth's orbit building up more and more speed using the slingshot effect. Along with Kepler, there was another guy by the name of Galileo. We've talked about him before, you've heard plenty. And his biggest contribution to motion said that an object doesn't do like Aristotle said. Aristotle said that if you roll a ball on the floor, it's going to stop because that's just what things do. Galileo did a famous ramp experiment where he determined that it didn't have anything to do with the ball moving. The ball really wanted to keep moving. It wanted to keep doing what it's doing. So Galileo is the one that realized that an object's natural motion is not to come to a rest like Aristotle said, but to keep moving in a straight line at a constant speed. This is where the idea of friction slowing things down first came into play. Before Galileo, it was just normal. Then Galileo said, actually, that's not normal. This is what's happening. Friction is happening. Right after Galileo was Isaac Newton, or Sir Isaac Newton, because he was knighted by the Queen. He came up with the 3 laws of motion, which we're going to go over. And the first quote I like for a couple of reasons. One, I don't know if you've heard before, if I've seen far, it is because I've stood on the shoulders of giants. That actually is a nod to Galileo. That's him not being arrogant and giving somebody else the credit that was due. I think that's funny because Isaac Newton was one of the most arrogant people. The book that he wrote explaining the 3 laws of motion, and as you'll see, they're ridiculously simple, he wrote in a very, very difficult way, not to be snobbish or anything, but the basic idea was that if you weren't smart enough to read it, he didn't want to waste his time with you. So he was just an arrogant jerk. Sorry. I like that last quote too there. I can calculate the motion of the heavenly bodies, but not the madness of people. Kind of cool. Okay, so Newton's laws of motion. I know you've had these before. I'm just going to go through them pretty quick. The first law is Galileo's law. Everything stays in motion, constant speed, same direction. You don't need a force to do it, to keep it doing that. So when we launch a rocket to another planet, to Mars, whatever, we only fire the rocket engines enough to get up and away from Earth, and where gravity is still there, but it's not affecting it much. And then it just coasts at whatever speed you gave it forever until something gets in the way. And the something getting in the way is typically us turning the rocket around backwards, firing the engines, slowing it down. When they went to Pluto, they decided not to do that because you would have needed a much bigger, heavier rocket for all that fuel to slow down. So they shot past Pluto at ludicrous speed and got a bunch of pictures. So that's why we don't have the entire surface of the planet photographed. And then it went on for other targets and stuff. So they wanted to go cheaper, so they didn't slow down and orbit Pluto. Which, I don't know. I would have preferred to see all that, but it's going to go see other things too, so not a total loss. The second law is the F equals ma that you've all heard before, and this is about the acceleration, and I always relate it to a shopping cart. If you have a lot of mass in your shopping cart and you want to make it accelerate, make it start moving, you have to apply a lot of force compared to a shopping cart that's empty. So force is related to mass, or if I look at force and I push on the empty shopping cart and the full shopping cart with the same amount of force, the one with less mass is going to accelerate more. So that's kind of one of those obvious duh things, but Isaac Newton put math to it and found out that he just found some fundamental stuff that missed people once he started doing that. The third one is the action and reaction forces. For every action, there's an opposite and equal reaction. My favorite quote on this one is the fact that you can't touch without being touched. From these laws, we say that Isaac Newton discovered gravity. Well, gravity is the generic term for things that make things fall. What Isaac Newton realized is that the moon, moving in a circle around the Earth, should go in a straight line at a constant speed. But it doesn't. It goes in a circle around the Earth, or more properly, an ellipse. So, in order to go in a circle, which is a form of acceleration, it has to have a force. So, the whole apple falling from the tree is probably not true. It's what historians have written, or what people have written, but historians believe that it probably wasn't true. What Isaac Newton realized is it was the force that causes an apple to fall, which we already called gravity, that makes the moon move in a circle. And then he realized that for every action, there's an opposite and equal reaction. So if Earth pulls on Moon, Moon should pull on Earth. And oh, yeah, that's what causes the tides. So he not only figured this out and thought it up, but the evidence had been there all along. The tides were perfectly matched to the moon's cycle, which we knew somewhat, but he explained how it worked and basically proved his laws of motion right there with that evidence of the moon causing the tides. So, incredibly smart guy. I don't know if I'd really want to meet him in real life, because, he was a jerk. I mean, look, he's taking selfies. There's a general math thing that applies to light and all sorts of things that says that when light shines, as the brightness of the light drops off according to the square of the distance, not just the distance. So we can see here that, if I can find my mouse, I can't find it. Okay. That is, you double the distance from a light bulb, the light intensity drops by a fourth. So double is 4, so 1/4, and then 3 times further, 3 squared is, did I say double? So double squared is 4. Maybe I already said that. But triple squared is 9, so it drops off by 1/9. You'll notice this with spray paint. The closer you hold it to the paper, the more paint gets on there. As you pull back, you get less paint. It follows what is called the inverse square law. The reason I'm bringing this up is because Isaac Newton realized that gravity follows the inverse square law. He said that gravity is proportional to mass. In other words, he's using his second law of business here and saying that the more mass there is, the more force. And what he stated right there is that all things have gravity. Now, this is what got Newton into trouble with the Catholic Church of the time, because the church taught that Earth is bad and, well, earthly, dirty. It would be destroyed during Revelations, and the only thing left remaining would be heaven, and they believed that everything outside of Earth was literally heaven. And Newton came along and showed that the moon, which is supposed to be a part of heaven, in other words, ultimate good and pureness, actually behaved like Earth, which is the epitome of evil and dirt and had to be destroyed and burned up. So it flew completely in the face of the church doctrine of the time and extended out to the other planets and everything. So Isaac Newton basically was saying, hey, you know that stuff that you thought was literally heaven and perfect and godly for thousands of years? No, it's just a bunch of dirt. So that caused some pretty serious conflict, but Isaac Newton was one of those guys that didn't really care. He was just more interested in the truth. And we still kind of grapple with some of that stuff today. We no longer think of space as heaven, but hey. He found that gravity uses the inverse square law, so the further away you go, it drops off. But if you look at your numbers there, R stands for the distance between the objects. If R goes to infinity, then the F, the force of gravity, goes down to 0, but never actually reaches 0. So think about that for a minute. You're staring at your screen, whether it's your phone or your laptop or whatever. According to Newton's laws, that thing, your screen, has gravity. And Newton's third law says every action, there's an opposite and equal reaction. You and your screen are being pulled on each other. You are attracted to your screen and it is attracted to you. Isn't that nice? If you look at the numbers here, it's ridiculously small. We can't even measure it. There was somebody in, I believe, the 1800s that actually measured the force of gravity between two regular objects. The objects, one of them was a 6-ton lead ball, which I believe you can still get at Walmart. They moved it under something and were able to detect the force of gravity between it, which is actually how they found the constant capital G. So, yeah, all things have gravity, and that's what was just so amazing about Newton's law here. Okay, so that's it for today. We'll move on with this next time.